Hi everyone. I thought I'd do a little video on superposition and interference, and in particular I want to focus on beats. When two waves move through the same medium, their amplitude combine. The resulting displacement of the medium is the vector sum of the displacements of the component waves. So we know that. That's called superposition. Two waves can move through the same medium, they will not slow each other down, and the medium will simply sum for those two waves. When two periodic waves of similar frequency interfere with each other, there will appear a periodic increase in the volume of the sound as they both constructively and destructively interfere with each other. So what does this mean? If you're sitting in a room and there are two speakers, and those speakers are both letting out a sound and they've got slightly different frequencies, well, you're not going to hear two different sounds, you're going to hear one sound. But that sound is going to seem to get a little bit louder, then a little bit softer. A little bit louder, a little bit softer. We call this beats. So if we had the wave function for one of those sounds, sound A, and the wave function for the other sound, which is sound B, they look very, very similar. But when you add them up, this is what we've got. So the combined effect of these two sounds at your location, where you're sitting in the room, will be, first of all, it'll be soft, and then you'll see the combined effect will be quite loud as the amplitude gets higher. And then it'll get small, it'll be soft, and then it'll be loud again. So this repeating pattern of loud and soft and loud and soft, this is beats, and it's due to the phenomenon of superposition. Now, if we have a look at these two frequencies, we've got pressure versus time graphs for the two frequencies, and they look very similar. Frequency A and frequency B look very similar in a pressure versus time graph. If we focus on frequency A, we can count up the number of cycles that go through in 10 seconds. We notice that there are 10 cycles that go through in 10 seconds. So that tells us the period of one cycle must be 1 second. And the frequency of this sound, A, is therefore the inverse of the period, 1 hertz. Looking at frequency B, and we count up the number of cycles that go through in 10 seconds, this time we see that it's 9 cycles go through in 10 seconds, which means that the period for one cycle is 1.11 seconds, and the frequency of this sound B is the inverse of the period, so the frequency is 0.9 hertz. If we get these two graphs and we lay them over the top of each other, frequencies A and B look like so. Now you can see where they match up pretty closely, and you can see where they are completely opposite. We say that where they match up at the 0-second mark and at the 10-second mark, we say that they are in phase. And where the two waves are perfectly the opposite of each other, we say that they are out of phase. When the two waves are combined, we notice that the amplitude becomes quite large, double either of the waves individually. It goes up to 2 on the pressure scale. And we see that it moves from a whole cycle of loud through to soft, back to loud again in approximately 10 seconds. So the period of this beat is about 10 seconds. If we look at the combined waveform over 30 seconds, we can see the pattern more clearly. So we see that at 0 it's loud, then soft at 5, loud at 10, soft at 15, loud at 20, soft at 25, loud at 30. So the sound gets louder every 10 seconds. So the period of this beat is 10 seconds, and the frequency is 0.1 hertz. Now we have the beats equation. The frequency of beats is equal to the difference between the two component frequencies. Now that's the absolute value of that difference. So whatever it might be, frequency A subtract B, frequency B subtract A, you might get a positive number, you might get a negative number. We just say it's the absolute value of the difference between the two component frequencies. In this case, we've got frequency A has 1 hertz and frequency B is 0.9 hertz. So the frequency of the beats is 0.1 hertz. Using the Beats equation, we get 0.1 hertz, and reading it off the graph and figuring it out that way, we also get 0.1 hertz. So let's try a problem. Two tuning forks, A and B, have frequencies of 500 Hz and 502 Hz respectively. When a third fork is sounded with A, 15 beats are heard in 10 seconds. When the third mystery fork is sounded with B, 5 beats are heard in 10 seconds. What is the frequency of this third mystery fork? Well, we start by comparing the mystery fork to fork A. We play them at the same time and we hear the beats. The frequency of the beats, we notice, is 1.5 Hertz. There were 15 beats in 10 seconds, so the frequency of the beats that we're hearing is 1.5 Hertz when fork A and the mystery fork are played at the same time. Using the Beats equation, we can then see that 1.5 is equal to the difference between the frequencies of the two forks. So the mystery fork is either going to be 1.5 Hertz more than fork A, or it's going to be 1.5 Hertz less than fork A. So it has to be 501.5 Hertz, or the mystery fork is 498.5 Hertz. They're the two choices. Now let's compare the mystery fork to tuning fork B. We play the two of them at the same time and we hear the beats again. This time we get 5 beats in 10 seconds, so that tells us that the frequency of the beats is 0.5 Hertz when you play fork B and the mystery fork at the same time. We use our Beats equation and we find that 0.5 is equal to the difference between the two frequencies. So our mystery fork has to be either 0.5 Hertz more or 0.5 Hertz less than fork B, which gives us the options of 502.5 Hertz or 501.5 Hertz. Now we remember when we compared the mystery fork to fork A, we got these two options, 498.5 Hertz or 501.5 Hertz. We see now that comparing the two forks to the mystery fork, there is one common result, and this has to be our answer. And so we figured out the frequency of the third fork, the mystery fork, by using the beats that we observed with two other forks of known frequency. I hope this was helpful.